Our next topic is reaction rate. And the first question that we need to ask ourselves in this topic is, what is reaction rate? What is reaction rate? Now, when you talk about rate, we are referring to speed. So when you talk about reaction rate, we are definitely referring to the speed of a reaction. To bring this closer home, a reaction shall involve two things. What is, and definitely products will be formed. Now, the reactants gets used up in the process, and products definitely gets formed in the process. So when we talk about the rate or the speed of a reaction, then we are referring to the speed at which the reactants are used up. So speed at which reactants are used. Then, of course, on the same note, we would say that reaction rate is the speed at which the products are formed. Mathematically put, of course, we can say that the rate of a reaction is equal to the change in the amount of reactant over the change in time. That gives us our working definition of a reaction rate. But you realize that this should be equal to the change in the amount of products over the change in time. Only that this is going to be negative. Why? Because the reactants are getting used up. So we could draw a very simple graph for that. So this is what you get over time in seconds. And this could be the concentration. Then the concentration of the reactant will be highest at the beginning of the reaction, and it decreases with time. Well, the concentration of the product is initially zero. It increases. Allow me to add to emphasize the fact that different reactions will take place at different rates. We have some very slow reactions. For instance, the rusting of iron. This is an extremely slow reaction. In fact, this is a reaction that we cannot hope to follow in a lab setup. It's like watching grass grow. But some very fast reaction, almost instantaneous. For instance, neutralization. There is an instantaneous reaction. Immediately you mix the sodium hydroxide with the hydrochloric acid, the reaction is over. So that again is going to be an impossible reaction to follow because it is very, very fast. So we shall choose reactions that take place at a moderate speed. Of that is a reaction between magnesium and hydrochloric acid. It will take place at a comfortable rate. Now, when you measure reaction rate, the first thing, of course, you'll need to, after you've chosen a reaction that takes place at a moderate speed, the next thing that you need to do is to identify a parameter. Identify a parameter, something that is observable, that you can follow in the course of the reaction. And these parameters could be volumes of gases. Volumes of gas, that is something that you can easily follow. You will have setups, maybe use a syringe as the gas is being produced. Then some follow experiment by measuring the mass the mass, maybe using a top unbalance, and you press the reacting substances on the top unbalance as the gases are produced. There is a change in the reading of the top unbalance that you can follow over time. Now, there are some reactions that will involve the formation of colored substances, like the reaction between hydrochloric acid and sodium thiosulfate to produce sulfur. So, and we will see that we will maybe place a cross, a paper mark with a cross down there. Then when you observe up there, the cross will be obscured. Another example of such is what you call the iodine watch experiment. The next question that we need to ask ourselves is, now, can the rate of a reaction between magnesium and hydrochloric acid be altered? Or are there some factors that would alter, that would lead to a faster reaction or a slower reaction? Now, in our day-to-day life, we have encountered that scenario. For instance, you discover that when you dissolve sugar in hot water, it dissolves faster. When you chew a sweet, probably it gets finished faster. When you light fire, you use small sticks, it is going to, the sticks are going to burn very fast, and the food goes bad in warm weather than in cold weather. So what are we saying? That you can speed up reactions, maybe by changing a number of parameters. And what are these factors that affect the rate of a chemical reaction? That is what we shall look at next.
So let's recap. The rate is reaction rate. Reaction rate is the measure of how quickly the reactants in a reaction change into the products of it. The rate of a chemical reaction can be measured in two ways. The first way is to measure how quickly the reactants, that's the substances on the left of the arrow in the equation, decrease. The second way is to measure how quickly the products, that's the substances on the right of the arrow in the equation, increase. Consider reaction. You can measure the gain in volume of the product, carbon dioxide, using an apparatus like this. You can watch. We plot a graph of volume of gas produced against time. The graph looks like this. As before, the rate of reaction at point A is given by the gradient at A, which is y over x. And the rate of the reaction at B is given by the gradient at point B, which is y dash over x dash. What do you think's happening to the rate of reaction as it proceeds? The rate of reaction decreases.
So what are the factors affecting the rate of a reaction? Now, before we answer that question, we will put across a theory that helps to explain how reactions occur. And that is what we call the cohesion theory. Cohesion theory. And there are two postulates of the cohesion theory. Number one point of the cohesion theory is that, as the name suggests, a reaction will not occur before a cohesion. So it is a cohesion is a precondition for a reaction. So reaction requires a cohesion to occur first. A reaction will be preceded by a cohesion. And that will help us to explain a few things that we have observed so far in the course of our study of chemistry. For instance, when you react red with dilute sulfuric acid, we are expecting to form red sulfate and hydrogen gas. We discovered that very little of that reaction will occur. And we did explain, we said that there is a formation of lead sulfate on the lead metal. So how does that go on to stop that reaction? You see, when the lead sulfate is formed on the surface, then the sulfuric acid, or the hydrogen for that matter, will be colliding with the lead sulfate. It will collide with the lead sulfate and there will be no reaction. So because a collision must take place between the hydrogen and the lead so that you can get a reaction. But now that has been coated, the hydrogen ions no longer have access to the lead, and that stops the reaction. Another thing that we have observed so far is that we have very few reactions between solids. A solid reacting with another solid. Now, if you look through your course, I think you will only come across one such scenario where a solid reacts with another solid. Let's say reaction we discussed in Form 1, the reaction between iron and sulfur. And even remember then, we had to heat the sulfur to melting so that we didn't actually have a solid reacting with another solid. Why is it so difficult for a solid to react with another solid? Because the particles in solid are only vibrating in position. There is no movement. Now, for particles to collide, one must translate. A particle must move from one place to the other so that it can access another particle. They collide, and that shall lead to a reaction. So in solids, then that is really not possible. Now, the second thing about the second postulate of the collision theory is that not all collisions will lead to reaction. Only those collisions that occurs with a certain minimum amount of energy that we call the activation energy. So the collisions must be energetic enough for them to lead to reaction. So those particles that do not collide with enough energy, they will just bounce off each other.
Let's say, imagine if I try to roll a ball up a hill, if I get enough energy into that system, the ball is going to roll down the other side. What if I don't have enough activation energy? Well, I can put some energy in, but if I don't have enough, then it's going to go back to where it was before. And so activation energy is how much energy you have to put into a system to have a chemical reaction occur. And we have two molecules, we'll call this A and B, and I were to launch A at B, what we'll find is that if I don't give it enough energy, then there's not going to be a chemical reaction in this one simple collision. In other words, you require a certain amount of energy for that reaction to occur. And you also have proper orientation. But if you do, then we can fire off that reaction.
Factors that affect reaction rate. Factors affecting the rate of reaction. Number one, the surface area. Surface area, of course, will affect reaction that involves solids. It's only solids with surface area that you can change. Number two, the concentration. This will affect reactions in liquid state, solutions and liquids. Then we have the pressure. But pressure only affects the reactions in gaseous state because it's only gases that you can compress. You cannot compress solids. You cannot compress liquids. Now, number four, the fourth factor that affects the reaction rate is, of course, the temperature. And these, of course, will affect reactions in all states, be it solid, liquid, or gas. Number five, again, there is catalyst. Catalyst will affect the reactions in all states. But how do these factors affect the reaction rate when we relate that to the collision theory? Now, allow me to say here that there are two ways in which you can basically increase the rate of any reaction. Number one, you can increase the frequency of collisions. You started with only 2 collisions per second, increase them to 3 collisions per second. That will increase the reaction rate. Increase the rate at which the particles are colliding with each other. Number two, even if the correlations were to remain constant, but what of if you increase the efficiency, if you can alter some factor so that the few correlations that you initially had are efficient, they are leading to reaction. So you start with 100 correlations per second, and now only 50 of them are leading to reaction. You retain the 100 correlations per second, but now you have 80 of them leading to reaction. That is another way in which the rate of a reaction can be increased. Either increase the frequency or retain the frequency but have the same more correlations leading to reaction. That is what we refer to as efficiency of the correlation. Now let's look at each of these factors and see how they affect the rate of reaction. Do they increase the frequency or do they increase the efficiency of the correlation? Now, the first factor that we take a closer look at is surface area. We start with a particle that is that size, and the particles that are exposed for collisions are only the particles on the surface. The reagent cannot get to the inside of that solid. Only the particles on the surface are exposed for collision. So supposing we break that into two. Now I have introduced more surface for collisions. Now I can continue breaking that. I am increasing the number of surfaces, that the number of particles that are exposed for collision. An increase in surface area increases particles exposed for collisions. Yeah, the particles that were initially hidden inside there are now exposed for collision. That means that they'll be more frequent. The collisions are going to be more frequent, and therefore we are going to have a faster reaction. So an increase in surface area will increase the frequency of collisions by exposing more surfaces, more particles for collision. Now, I think that is a common when you consider glucose and sugar, which when you put glucose in your mouth, it disappears very fast because it has a larger surface area. There are smaller particles as opposed to the sugar where you have bigger particles. It will take a longer time to dissolve in the saliva. Now, for those of us from the village, if you want to light fire, you use small twigs. They are going to catch fire very fast. And of course, that means that they're going to be used up even fast, as opposed to big logs that will take quite some time to burn. Why? Because the small twigs have a larger surface area. In fact, I want to underline the fact that reactions that involve with ions are fastest for two reasons. They have maximum surface area, and number two, they will accelerate each other. Therefore, the collision is going to be, they're going to collide with a lot of energy, and that therefore they have more than the minimum amount of energy. So that also may have the effect of increasing the efficiency as far as the solutions are concerned. But to recap, the surface area, you increase the surface area, you increase the number of particles that are exposed for collision. That increases the frequency. Now, the second factor that we have there is the concentration. And how does the concentration increase the rate of a reaction? Right? Let's think of a scenario where we are using, say, 1 molar hydrochloric acid, for instance, reacting with say, magnesium ribbon. We have, let's say the particles are that that space, and the magnesium ribbon is right there. So when you increase the concentration, what does that mean? You are going to have more particles. Now, I don't want to have a bigger container. I just want to have more particles per unit volume. And note, it is more particles per unit volume. The unit volume is very critical. It's very critical. When you have more particles per unit volume, now let me still put the magnesium ribbon right there. So the particles will have to move only a short distance to collide. They have to move only a short distance so that they can get to the magnesium, and therefore the frequency of collision will be increased. The frequency of the collisions will increase because the particles are closer to each other. They are very close. They only have to move a short distance to get to the magnesium and collide with it. Now, let me get back to the number of particles per unit volume, because supposing I have 50 cubic centimeters of 1 molar, capital M, of 1 molar hydrochloric acid, and now I have 100 cubic centimeters of 1 molar hydrochloric acid. Definitely, I have more particles here. I have more particles here. I have fewer particles here. But the number of particles per unit volume are the same. We are not interested in the overall number of particles. We are interested in the number of particles per unit volume. So an increased number of particles per unit volume is what affects the reaction rate, and not an increase in the number of particles. So if I use 50 cubic centimeters of 1 molar hydrochloric acid, another person used 100 mils of 1 molar hydrochloric acid, the rate of a reaction should be the same. They should react at the same rate because the number of particles per unit volume are constant. So always remember that an increase in concentration increases the number of particles per unit volume. That is pressure. Now you can pause to think, how will an increase in pressure affect reaction rate? I hope this is what we are coming up with. Now, when you increase the pressure, now these are the number of particles that you have. Maybe you have a plunger here and you press it down. So these particles are pressed to this new volume. So the same number of particles but occupy a lower volume. What does that mean? Now the distance between the particles is decreased. You decrease the distance between the particles, therefore there will be an increase in the frequency of the collision. So this one increases the frequency of collision by bringing particles closer. Bring the particles closer to each other, so they are going to collide more often, and that of course will increase the rate of the reaction, but only if the reaction involves gases. The factor number 4 is the temperature. The temperature. How does an increase in temperature affect the reaction rate? Now, it has twofold effect. Number one, an increase in temperature will increase the kinetic energy of the particles. The particles are going to be moving faster. They're going to be moving faster. Therefore, they are going to collide more often. The particles will move faster, collide more often. When they collide more often, then they are going to lead to faster reaction. So increase the frequency of the collision. So increases kinetic energy, therefore more frequent collisions. So increasing the kinetic energy will lead to more frequent collisions, and therefore the rate of the reaction will increase. Now, the other thing that will happen to increase the temperature is that the kinetic energy, the energy of the particle, each particle has a lot of energy. You increase the energy per particle. What does that mean? that when the particles collide, they'll be colliding more energetically. So we have more of the particles have more than the minimum amount of energy that is required. That is what we call the activation energy. More particles will have more than the minimum amount of energy. So more of the collisions are going to lead to reactions. So the increase in temperature can increase the frequency of the collisions. The particles have more kinetic energy, they collide faster. Again, it can increase the frequency of the collisions, the efficiency of the collisions. Why? Because more particles have more than the minimum amount of energy that is required to react on collision. Finally, let's look at a catalyst. And from our Form 1 work, we said that a catalyst is a substance that alters the rate of a reaction but is not used up in the process. That is what a catalyst is. And we have come across quite a number of catalysts. Like we talked about the manganese peroxide in the catalytic decomposition of hydrogen peroxide. We have talked about platinum in the contact process, iron in the Haber process, the banana, of course, the contact process, so we could use vanadium 5 oxide. Those are some of the catalysts you come across, and you will come across a number of them. But how does a catalyst increase the rate of a reaction? Now, a catalyst will provide an alternative route. And the route is not shorter, you can't measure in kilometers. So it's an alternative route that requires less activation energy. It provides an alternative route that requires less activation energy. So that if you can draw an energy level diagram with so if this is this is energy and this is time. So this is the activation, the minimum energy that you must supply to, so that you get the particles here to what we call an activated complex, the activated state. Now you supply energy until you get to that point, then the reaction will just occur. This is what we call the enthalpy of a reaction. But if you use a catalyst, then you have a lower energy barrier. You have a lower energy barrier. This is the activation energy that you shall need for that reaction. So if you now need less energy, what does that mean? More of the collisions are going to lead to reaction because the energy that you need is less. It's like if you like they do with the admission board, the university admission board. If they lower the pass mark to the university to a C+, a certain number of students will make it to the university. But what about if they raised it to an A? Yeah, you are going to get fewer students. Less students have the minimum entry requirement to the university. And it is the same thing, yeah? Now, these two particles, initially when they collided, they could not react because they didn't have enough energy. But now you have a route that requires lower energy, so that even these ones that did not qualify for reaction then are going to lead to reaction at this point. It's like you are jumping in high jump, and you raise the bar. You raise the bar. Less students are going to be able to jump over if the bar is raised. And that is what a catalyst will do. It will lower the bar so that less and more of the particles are going to have more than the minimum amount of energy to react on collision. Note that we have some catalysts that we call inhibitors. That is the negative, they slow down rate of reaction, like the preservatives, the sodium beta bisulfite in the preservation of trees and all that. They are They are negative catalysts, and you can come across a number of other negative catalysts. But will negative catalysts, do they work by increasing the activation? And the answer is obviously no, because when a reaction is, when you are faced with two scenarios, one that requires more energy, another one that requires more energy, there is no way you are going to take the one that requires more energy. So if an inhibitor is working by raising the energy barrier, then it's not going to work at all, because the reaction will prefer to take the route that requires less energy. So how do inhibitors work? Inhibitors will work by consuming the activated complex. By consuming the activated complex. So the reaction will start, get to that point, then the inhibitor will take it back, get it back there. So the downward flow will not take place because the activated complex has been consumed by the inhibitor.
Can now conclusions occur when two or more molecules collide with each other and must possess enough activation energy, which is the minimum amount of energy needed to start a reaction. Temperature. Once a substance is heated, the particles move more quickly and they have more kinetic energy. The particles collide more often and more of the collisions are successful. The rate of reaction, therefore, increases. Particle size. If the surface area of a reactant is increased by cutting the substance into small pieces by grinding it into a powder, more particles are exposed to the other reactant, increasing the rate of reaction. Presence of catalyst. Catalyst lower the activation energy of a chemical reaction and increases the rate of reaction without being consumed in the process.
The next thing that we shall do this topic is to experimentally determine some reaction rate. We shall do some two virtual experiments. We expected to follow through, correct the data and record it. Then we shall use it to draw some rate curves. In this particular first case, we shall follow the reaction between hydrochloric and sodium thiosulfate. Now the reaction shall be something like this. Sodium thiosulfate. This shall react with hydrochloric acid to form definitely sodium chloride, sodium and chloride. Then we shall get some sulfur peroxide and sulfur. This will be in solid state. I think I can balance the equation. The sulfur obtained shall be in solid state. Now, being a solid, therefore, what will happen is that when I place the reacting vessel on paper that had initially been marked across, when I get sufficient amount of the colloidal sulfur, the cross will no longer be feasible. So it will be obscured. So I want to find out the time taken for the cross to be obscured at different concentration. And the concentrations are right there. So I will start with a beaker that contains 50 cubic centimeters of 0.15 molar sodium thiosulfate, to which I'll add completely no water. Therefore, that solution will be actually 0.15 molar. Then 2/3, so that is 0.15 molar because I did not dilute. Then 2/3, I will add 5 cubic centimeters of hydrochloric acid. Then once the reaction occurs, sulfur will be formed. Then when I get sufficient amount of sulfur, the cross will disappear. The cross will be obscured. I will record that timer. And now we repeat the procedures with 40 cubic centimeters in beaker number 2. beaker number 2, although in this particular case I will just use one of the beakers, so I'll be adding the syringe to one of the beakers. But the solution will be prepared as shown. So 30, 20, and 10 with 10 cubic centimeters of water, with 20 cubic centimeters of water, with 30 cubic centimeters of water, with 40. Note that I'm ensuring that the amount of solution remains constant, because the intensity will depend on the height above it. So I will have to keep the volumes constant. Then with 5 cubic centimeters of hydrochloric acid throughout 5.0, 5.0, and 5.0. I could put the units here so that I don't lose the decimal mark, and then I will be recording so that I will get all the sets of data. So let's start. Let us now start with the experiment. Experiment number 1. That is the experiment consisting of 50 cubic centimeters of 0.15 molar sodium thiosulfate, no water. I add 5 cubic centimeters and start the watch, and then I'll record the time taken for the cross to be obscured. Get to the second experiment consisting of 40 cubic centimeters of sodium thiosulfate, 10 cubic centimeters of water. Then let's see how long the cross will take to disappear. Now that beaker consists of 30 cubic centimeters of sodium thiosulfate with 20 cubic centimeters of water. Start the watch and stop when start the watch immediately you mix the solution, and stop it when the cross disappears. The next one consists of 40 cubic centimeter or 20 cubic centimeters of sodium thiosulfate and 30 cubic centimeters of water. You will start the stopwatch when we mix the two. and then you stop it when the cross disappears. And finally, we have a beaker consisting of 10 cubic centimeters of sodium disulfate, 40 cubic centimeters of water. Start the watch when we mix the two, and then stop it when the cross is obscured. Thank you. I hope we've filled the table with some data. You can fill the table in whole numbers or in one decimal place, but avoid using something like that, 1 minute and 30 seconds. There's no such decimals. The time should be recorded in seconds. Let's ensure that the time is in seconds. So let's convert whatever time that you have in seconds. So what do I want us to do? The first thing that we should do is calculate the concentration. Calculate the concentration of each of those solutions. And secondly, let us find the rate, where the rate is given by 1 over time. 1 over time. So let us work out 1 over time for each of the 5 experiments. So if the time is 23 seconds, so that is 1 over 23. Don't leave it like that. Work it out in 4 significant figures and record it in your table. The data obtained in that table, let us draw a graph of concentration in the y-axis or the vertical axis against time in the horizontal axis. Remember the rules in drawing a graph, that your scale should be big enough, that is the size of the graph. The scale should accommodate all the values, and the scale should be consistent. That is what we learned in solubility and solubility curves. Now let us label the axis also and put the correct units, like the units this time is seconds and concerning most per liter. Let us plot as accurately as we can, and let us obtain a curve. Use freehand to draw your curve, and draw the curve of best fit. Being experimental data, some of the points may not be on the curve. When that is done, on another graph paper, we will draw the graph of concentration on the y-axis against time, against 1 over time. This is what we refer to as a rate, against 1 over time. Now, it is hoped that you will get a straight line that should pass through the origin. So note that this one must start from 0 that side and 0 the other side. So the graph will be extended to the 0. So this one you must draw from the first plot to the last plot. Don't extend, but this one must be extended so that it gets to the 0, 0. So the question of breaking axis does not arise here. For this one, you don't have to start from 0. In fact, if you start from 0, you may lose the scale mark because the graph will be too small. But for the other one, you have to start from 0, 0. The graph of 1 over t is hoped that it is going to be a straight line, that is per second, versus the concentration. It will be a straight line graph passing through the origin. So how does it go through the origin if you did not start from 0, 0? It is mandatory that you start from the 0, 0. We continue with the experimental determination of reaction rates, and in the next experiment we shall study the reaction between hydrochloric acid and marble chips. So now when you talk about marble chips, we are talking about big pieces of calcium carbonate, the granules of calcium carbonate, as opposed to the powder. So when you get big pieces of calcium carbonate, we call them just carry out the experiment and record the mass every 2 minutes. went through the same procedure, and that is the data that I got. So I want to draw a graph, the graph of mass against time, and that is what I will call a rate curve. So the first thing I will do is, of course, draw the axis, and I should use a pencil. The nature of my data, and the fact that so it is not mandatory that I leave this one box, but the nature of my graph paper dictates that I leave space for writing, because I will not be able to write on both the labeling and the. So this is time. The time is in minutes. So again, I can start and can write the zero there, but you need to be very careful about that zero. So what will I be drawing here? It is the mass of calcium carbon, or the mass of the mixture, carbonate plus the acid. So mass in grams, the mass recorded in grams. So I will adopt a scale of 3 centimeters to represent 2. The idea is to have as big a graph, so that should be 4, 6, 8, 10, and 12. Now I have the minimum value that I have to plot is 114.72. The maximum value to be plotted is 116.02. Subtracting that, I think that gives me 1.3. How many boxes do I have in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. I have almost 26 boxes, so 1.3 to be distributed in 26 boxes, that gives me 0.05. So each small box should represent 0.05. So how do I draw that? I need to break this axis because I have a big zero there. Otherwise, if I don't break, I will lose the scale mark and even the plotting. So the first I will start with 114.7. Now one small box to represent 0.05. So I can use 2 small boxes for 0.1. So the other one will be 114.8, 14.9, that is 115.0, 116.0. Yeah, that's 02. I can't get to 02. So now we plot the value corresponding to 0 is 0.02. Yeah, right there. Corresponding to 115, 115.67, 115, 115.6. Note that I need to be as accurate as my graph will allow. So 97, 97, 97, 95, then 2 more. Not around it's exactly there. 10, 114.84, 8884, so not yet 5, just 1 less than that. Note that I'm using crosses. They can easily be seen. 114.72 7 and 7, 4, 7, 2, 7, 2. Yeah, when I look at that, I want to find out whether it is a straight line. And sure enough, this is not a straight line. So I draw a curve. So I use a pencil, draw a smooth curve. How smooth is smooth? Now let us use the graph. You may be asked to determine the rate of a reaction between some 2 points, or you may be asked to get the rate of a reaction at a specific time. How do we get the rate of a reaction between the first and the fourth minute, for instance? Let's use the first and the third minute. Getting the rate of a reaction between the first and the third minute. The first and the third minute. Now, this is what I do. Get to your graph. Now, where is 1? 1 is in between. Where 1 meets the graph, that is the point. And then the third is right here. So to avoid paradox, it's always advisable to show. It's easier rather than struggling to see. So that is what we have. The third minute, where are you, Mr. Third minute? Yes, there you are. Join, so that I can now. It doesn't. Otherwise, you'll have to struggle to keep your eyes open if you don't draw. So there, you join that point to that point. Join the 2 points, and now you'll do exactly that. Then I need to get the gradient of the line joining those 2 points. So I'll just extend the line so that I can show what I am doing. So there we are. So what is the coordinate of this point? Allow me to make that correction for the first one. It should be 115.8 minus 15.48. So I'm using this point and the other point there, the point corresponding to 3. So it's 115.8. That is the rate of the reaction between the first and the third minute. So you just join the 2 points, then get the gradient of the line joining the 2 points. Now, what about if you're asked to get the rate of a reaction, say, during the fourth minute? Yeah, the rate of a reaction during the fourth. How would you get that? Now, yeah, we only have 1 point, and the rate of a reaction is the change in mass over the change in time. That is from our definition, the change in quantity over the change in the other quantities. Because all you need to do is to draw the tangent to the curve at that point. So the fourth minute, draw the tangent to the curve at the fourth minute. And there we are. That's a tangent to the curve at the fourth minute. Select some good values. I can see that, okay, the fourth is a good value, definitely. Yes, I have identified some good points. Yeah, like the point around here, the one, point one, and the 4 definitely. So change in y 115.66 corresponding to 1, take away 115.35 4, and when I 0.103 grams per minute. That is the rate of the reaction during the fourth minute. Having drawn the graph now, and we are calling it a rate curve, we can be asked to get the rate of a reaction, and the rate of a reaction may be instantaneous or may be an average rate of a reaction. I have already done the rate of a reaction between the first and the third second. So the first and the third minute. So what do? Just join the first to the third, and I did that already. Just join that and get the coordinates of those points or any other points that you feel are appropriate. Then use that to work out the change in y over the change in x. I got 115, 1 and 115 as a coordinate of that, 115.48 and 3 as a coordinate of the other point, and I worked out the gradient to be negative 0.16 grams per minute. Then you may also be asked to work out the rate of a reaction at an instant. Like I worked out the rate of a reaction at the 4th minute. How do you get a reaction, the rate of a reaction at a particular point? Yet you need a gradient. You need a gradient, so you cannot get a gradient with only one single point. So what do? Draw a tangent to the curve at that particular point, and that is what I got. Draw the tangent to the curve at that particular point. And a tangent is a line that touches a curve at one point only. Then select some good points on the tangent. I decided that the 4 and 115.35 is a good point. Then I also went for 1 and 115.66. So I want to use those 2 points to get the gradient, and I've worked out the gradient to negatives 0.103. Now when you look at that, you realize that the gradient of the curve between the first and the third minute is higher than the gradient of the curve at the 4th minute. What does that mean? That the rate of a reaction is decreasing. The question we ask ourselves is, why should the rate of this reaction be decreasing? We go back to the factors that affect the rate of a reaction. One of them, we are using the hydrochloric acid. It is getting used up, so its concentration must be decreasing. So whereas we started, we say 1 molar, or actually it was 5 molar hydrochloric acid at the beginning. So by the time we get to the end of that reaction, it should be maybe 4 molar or something like that. A bit of the acid will have been used up. So the rate of the reaction will be decreasing over time. I would expect this curve maybe eventually to flatten off, but after quite some length of time. The last thing that we need to consider in this topic is the idea of sketching rate curves. Like in the example that we have just attempted, where we got a graph that looks like that, when we plotted the mass of whatever was remaining in the conical flask against it, we got a graph that looked like that. And you may be given different conditions, and you're asked to to sketch a red curve on the same. There are so many options. For instance, the graph that you want to plot may be exactly on the original curve. For instance, like if it was a reaction where you're using a catalyst and you're told, supposing you double the mass of the catalyst, you don't affect the reaction rate by increasing the amount of a catalyst. It's the quantity. You just need a trace of the catalyst for the reaction to be catalyzed. So you can get a graph that looks like that. That is another option. Now, what types of reaction is this? Now, this is, of course, a reaction that is producing less. The mass obtained is less.